Okay, welcome back. A few quick announcements. So we do have the midterms graded. Nothing more will be said until the end of class because you won't pay attention. But we'll get them back right after class. Maybe like, I don't know, right out here or something like this, just so we're out of the room because I think they have the seminar coming in. The other, well, so I guess I'll say that the regrade policy basically is if you find something you think should have been graded differently, then you have to come drop it off and tell us what you think was wrong. We'll actually regrade the entire test. So if we could find points to take away as well as points to give back. So do so at your own peril. That's the only way we can sort of keep it reasonable. The other announcement is that the problem set, since we spent all the weekend grading, the problem set will be released on Thursday, also since most of you don't start till Thursday anyways. So apologies, but we'll release the problem set by Thursday class instead of today. But we'll keep it on the normal schedule. It should be okay. Yes, those are the announcements. Anything else? Okay, great. So today we're going to talk about nominally humanoids, but maybe more generally we'll talk about what you can do if you have a highly articulated walking robot. Okay. You could have told me that. It was up before. Yeah, I think it was up before. There we go. Thank you. Don't hit help. It's the last thing you want. Okay, so today let's talk about, the topics we'll talk about are nominally discussed in the humanoid robotics literature, but really I think they're valuable for any sort of highly articulated, you've got lots of joints, lots of motors. Articulated. Still recording. Yes. Thank you for checking. Okay. A highly articulated, let's say, legged robot. Okay. All right. So we've talked about passive walkers and hopping robots so far. And these really do paint for you, I think, the picture of the fundamental dynamics of walking, right? So I think the story about the exchange of energy with potential and kinetic, the prevalence of the dissipation to the ground at a contact, and the way that you have to think about contact in your planning and control. These are really the fundamental stories in walking, okay? But if you look at that literature and you look at what we've talked about so far, and then you look at the sort of published literature on walking robots, there's this huge disconnect, right? The things that we haven't talked much about yet, like the zero moment point idea that that I mentioned, these are what right now dominate the literature in walking robots. So the goal for today is to put these two together, to try to penetrate a little deeper into the idea behind the walking algorithms that people are fielding on big humanoid robots today, how we can understand them in the light of the optimization-based tools we've already developed, and just make sure you understand that story. And we'll give some fun demos. Okay. All right. So. Before we start actually talking about legs, I want to have a different model in your head, okay? So maybe call it a hovercraft or a satellite in gravity. But I want you to think about this. I want you to think about, you've got some rigid body, okay? It's flying through space. It's got a mass. It's got an inertia. Okay? And you have some thrusters. Okay? So I don't know what a thruster looks like, but something that gives me a force. This is, maybe I'm pushing on the world, but it's pushing on me in the other direction, obviously. So I've got something with thrusters coming out, and I've got gravity coming down. And maybe I'll have more thrusters than that. We'll see, okay? So this is, it's just a toy model, and that's meant to be some rigid body, not necessarily a square. Okay? And our goal for this toy model here is to move the center mass, this mass and inertia. You move your rigid body around, right? It's to move, relocate or stabilize those positions. So let's give it a coordinate. We'll say maybe I'll do it in the XZ plane just to remind us that there's gravity. XZ, and then we'll give it some angle of the rigid body. Data. Okay. So we want to go to move around and stabilize the position, X, Z, and theta. All right, so the cool thing is I can write the dynamics down for this. It's pretty easy. Okay, so I've got mx double dot is just the sum over all the thrusters of the x component of the thrust. F equals ma, right? Z dynamics are similarly simple. It's the Z component of those forces, and then there's a gravity force too on the Z direction. And then there's some term giving me my angular acceleration, rate of change of angular momentum, which is going to look like Ri cross Fi, and the y component of that, if you will. So this is, the thrust is happening at a vector Ri, R1, let's say, and R2. So that's the location of my forces, right, is described relative to that point. Yeah? This is a cross product. This is a vector. And I just want this is also a vector, of course, and I want the y component of that. The one coming out of the board. Yeah? Okay, so if I think of this as a control problem, maybe my control input is my forces. I can control the forces. And as far as things go in this class, this is actually a relatively easy control problem, right? So what do you notice when you look at this? Well, first of all, it's a linear system. Well, it's an affine system. There's some extra terms coming around, right? So this is the dynamics are affine. Okay. So what does that mean? So that means that I could actually stabilize this thing with LQR if I wanted to, right? In fact, if I have some desired trajectory that I want to stabilize, I could do TV LQR or right, time varying LQR. Yeah, I mean, you could ask it. Maybe everybody's got the same question if you want. But.
You were just asking because the way that the forces are drawn, it looks like they're almost going to the center of mass.
It's like an reverse rotation if they're not like
That's right. Yep. And in general, they're arbitrary right now.
Yeah.
Yep. For the toy model. Okay, and then maybe I can make it more interesting. So maybe the thrusters aren't very good at sucking; they're only thrusting. So maybe I could I could say, for instance, that all Fi had has to be, maybe they always have to be pointing out. However, I want to write that. But maybe I want to have some directional unilateral constraints on. And then I could still do some nice planning. For instance, I could do, if there are linear constraints on this, if there are bounds, let's say, I put it under element-wise, have some limits, then I could still do nice planning and control with this, right? With for instance, the constrained, we talked about the existence of linear model predictive control as a solution for linear systems with constraints. Okay. So in general, this is a relatively easy control problem. Okay. And you could imagine that that maybe if I've only got 2 thrusters, then it might be hard to sort of balance myself with the 2 thrusters. But again, I'll know if I can stabilize it or not because it's a nice linear system. Yeah?
What's MPC, sir?
This is model predictive control. I really only talked about it to the extent that I mentioned that I wasn't going to talk about it. But it is the extension of sort of LQR for things that have inequality constraints. Okay, so you guys like that model? We got a spaceship or whatever, but it's in a gravity field. Got some thrusters out there. Easy to control. All right, so let's make it a little bit more interesting. Yeah. So let's say I've got now. I still got my thrusters. Okay, but now let's say I have way too few thrusters. Let's say I've got let's say I've got too few thrusters. Maybe I only have 2 and I'm trying to stabilize in three dimensions or whatever, okay? But I'm allowed to move my thrusters, all right? That's the new game, right? Okay, so with one constraint, right? So I mean, if you imagine it as a spaceship, and you send your crew down to move the thrusters, maybe they don't like moving a thruster when it's turned on. So let's say there's a rule that you're allowed to move the thrusters if you want, okay? But you have to turn them off if you're going to move them, okay? That's our game, right? All right, so maybe I'll write that down as I have a model now where the control inputs, same model I wrote before, but the control inputs might be F1, F2, but also R1, R2, for instance. And maybe I'll put in some constraint, for instance, that the force has to be 0 if or the velocity has to be 0, which you could write, for instance, like this, that either the force is 0, the magnitude of the force is 0, or the velocity is 0 in order for that constraint to be held. Okay. But this suddenly is a much harder problem because, well, this is a non-convex constraint. This is an either-or constraint, right? So if I were to plot it sort of in my, R dot and F, right? So I'm allowed to have F be positive, or I'm allowed to have velocity, but I'm not allowed to have anything else, right? So you could think of that as that's a non-convex constraint, right? So something in here, in the interior, the combination of those 2 points, the convex combination of those 2 points is not necessarily in that set, right? So that's a harder planning problem, a harder control problem. Okay, but a good one, right? If I've got a spaceship with moving thrusters, that's a sort of problem you'd like to solve, right? So, and we have some tools to deal with that. And you can do a variation. Maybe it makes sense to write the positions of the thrusters in the local frame. Maybe it makes sense to write them in the world frame. That's a simple variation, okay? But this is sort of the problem I want you to have in your head. You're flying through space. You don't have enough thrusters to do everything you want to do, but you're allowed to move them, okay? All right, so now let's add even a few more constraints to it, right? So what if I could only, let's say, in addition to not being able to move the thrusters to turn them on when they're moving, but let's say I have some additional constraints like I'm only allowed to turn them on when they're in a certain region. Okay, so let's say when I put my thruster in a certain region, then I'm allowed to turn it on. Okay, but if it's outside those regions, not allowed to turn it on, right? Yeah.
What force do we use to move the thrusters, and is there limits on how fast we can do it?
So we could start putting down like a velocity limit on r dot would be a reasonable thing to add. Yeah, that's a good thing to add. Maybe I can call it Vmax or something, velocity max. Good question. Otherwise, it's easier again, right? Okay. So now you could sort of think about, let's say maybe I'm flying through space and I can, the game is going to be, okay, let me put my thruster here, turn it on for a little bit. Maybe I'll move it over here, turn it on for a little bit, move it over here, turn it on for a little bit. All right, can you sort of see where I'm going with this? It's hokey. But I think it's exactly the right way to think about walking. I think this is exactly the right way to think about walking. Everything else is confusing. This is the problem in walking. You have a center of mass, you're moving through the world, right? And you have feet, okay? Your feet can produce force, okay? But they don't produce force when you're moving them to the next spot, right? They can only produce force when you got them stationary. You can push on the ground, okay? And guess what? There's constraints on where I can put my foot. Actually, when I stop my foot in the middle of the air, it's not so good at producing force, right? There's a few places I can put them down in the world where I can trust them to produce force for me, right? This is the walking problem, okay? A hokey version of it, yeah? So here's my, this is really the fundamental problem in walking. Think about a robot with massless legs. So now I've got my robot, which has a mass and an inertia, right? And he's got some legs coming down with triangle feet, because I'm not an artist, right? And he's got another really long leg over here that, maybe he's right? So when he's in these configurations, he can produce force. You think of it as him pushing on the ground or the ground pushing on him, whichever view you like, as long as we get the equations of motion right. But let's just keep drawing it the way I was drawing it before. Okay? And when my leg is swinging through the air, no force. Okay? And yes, there's going to be some limits on how fast I can move my foot to the next spot. This velocity limit that Pete asked about, absolutely, right? And now you can see the sort of the constraints are there might be more natural descriptions on the constraints of the forces I get out. For instance, I might have friction constraints. So for instance, maybe the magnitude of my forces parallel to the ground has to be less than or equal to the normal force perpendicular to the ground. So this would be a simple model of friction, a friction cone. Okay, well, this is a coefficient of friction. Why is that a friction cone? That says my forces at my points can only live in some cone like this, right? It lives in that but I can't expect to get, if I'm not putting any weight on the ground, I can't expect to push horizontally in the ground. It's a reasonable model of cooling friction. That is the cooling friction model. Okay, so so good. So this is my problem now, and the dynamics I wrote down are exactly the same as the satellite problem, right? I just have a couple more constraints on my forces. Maybe I have a constraint on how fast I can move the foot, but that satellite problem is really the walking problem. Okay, so far I just talked about a single rigid body. So what if I want more than just a single rigid body? If I had mass in my legs, for instance. So I'm just going to change my mass. My point mass here is going to turn into the center of mass, which is going to be configuration dependent. Okay, and my inertia, the generalization, we'll call it the centroidal momentum matrix. Okay, and it's again configuration of the robot dependent, where my center of mass is. But actually, otherwise, the equations of motion I gave you on the previous slide are basically unchanged. Okay, so I could do this. I could talk about the dynamics of the center of mass using those same linear equations, plus constraints on forces, and then if I have to start moving them, possibly constraints on R dot. Yes.
You're not worried about like what the state of the angles of all the joints are, just because we have really powerful actuators. Or,
That story's coming, but it's not here yet. So I'm saying Q is all the joints of my. This is
yes, that maps into the center of mass and stuff. But
Exactly.
We're not worried about controlling Q directly, only how it affects.
Oh, good. So I'm not specifying any objectives for my joint angles yet. I'm just saying that I can describe the dynamics of my robot, my center of mass, and centroidal momentum with simple equations, right? And you're right. So that means I haven't specified in my design yet anything about the joints. Good. Okay, so this is not, I want to distinguish. Some people, I think, talk about these equations that we're going to get into, the ZMP and the center of pressure and all these things, as a simple model for walking. It's not a simple model. This is the governing equations of the center of mass of my robot for the real robot. There's no simplifications made here yet, except that I'm only describing the dynamics of the center of mass. I'm not describing the dynamics of the joints. Okay? Good. All right, now a couple special things happen. If I'm willing to make the terrain flat, then that's an important special case that we can look at, okay? But I do think while we're talking about this, you should be thinking about how would I write down that problem of, moving my satellite thrusters to the next spot so that I can do it. I mean, it's sort of, in some ways, it's much easier than thinking about a full walking robot, but it's still a problem that we haven't given you good tools to solve. It feels like there's a discrete decision to make, which is to pick up a foot and move it at some point. I sort of know how to solve the control problem if I keep my feet still. That's just, I could just do the, if I'm moving my feet relative to my body, maybe I have to do the nonlinear version. But we have sort of a control design problem we're used to. But this idea of stop, pick up, make a discrete decision to put it down over here, that's something we haven't really given you good tools for yet, right? So you should be thinking about that problem and how you'd be addressing it. So let's continue to understand the equations of motion and the implications of the equations of motion in the special case of flat terrain. So now I've got my point, or my center of mass and the inertia around the center of mass, and I've got flat terrain. Okay, and let's say I've got forces that all originate from the terrain. Okay, force 1, force 2, force 3, force 4. Not sure what happened to force 1 there. Okay. There's a couple things that we can write down that describe the dynamics, sort of very natural constraints, right? So if I want to summarize the constraints of all these forces with a couple sort of simple quantities that get rid of some of the details, it's going to be very easy to do that in the flat terrain case. Okay, so for instance, since I know that all of the x components are individually less than or equal to the z components, I'm going to say, by the way, that all of the z components are greater than or equal to 0. Okay, I'm only allowed to push on the ground. I'm not allowed to pull on the ground. Okay. If I know that all the x components have to be, in this friction cone, then that implies some things about the net force, right? So that I could somehow start writing summaries of these forces. The sum over all these Fix is also going to be less than the sum of the Fiz's. Okay, that's going to be important. Why is that important? Because that implies something about my center of mass dynamics, right? So remember, my center of mass dynamics were just sum over I Fix, right? Implies that my x double dot simply cannot move faster to, I cannot accelerate faster than z double dot plus g. Okay? Let's make sure we can get that. Okay, so can you work that?
Visually, that's like the bottom.
So exactly, this is exactly right. So each of these individually has a friction cone associated with it. And what that implies is that I have somehow a cone on my accelerations of my center of mass. That's exactly the right point. So is that somehow I can summarize the total constraints on these forces on a simple constraint on my center of mass acceleration, right? And that might be a little conservative because because of my inequalities here, but this is certainly a constraint on the total acceleration of my center of mass.
So
Yeah.
do we have 4 feet here, or do we have like 2 vectors per foot?
Agnostic. I'm not going to judge you if you only have 2 feet. I'm not going to, more legs are normally better, but whatever you want to do.
Can you just model the entire contact patch as just one force vector?
So we're going to think about that to the extent to which we can do that, right? So you could absolutely you could think of this as a single foot that has, if you're wearing cleats, you could think of this as a single foot here, or you could think about this as 2 legs coming down and making contact at 2 different points. I'm agnostic. So I guess I've drawn a 3-footed beast, but the point is it doesn't matter, right? Okay. The fact that there's more constraints we can write down, right? The fact that I can only push on the ground, that's going to imply that the total, obviously, the total vertical force has got to be greater than or equal to 0. So what does that mean? That means my z double dot has got to be greater than or equal to negative g, right? Nothing I can do, if I'm only allowed to push on the ground, nothing I can do will accelerate my center of mass towards the ground faster than gravity, right? That's probably a good thing. But that's certainly a constraint, okay? Now there's another magic constraint, okay? There's a magic constraint that we'll define. So let's define a point on the ground here to be the center of pressure, okay? And I'll define that to be sort of a weighted average of these forces, okay? So sum over I, Ri, the x component, Fi z, over the sum of I, Fi z. Okay, so I'm just going to be looking at the z component of those forces and taking a weighted average, and that gives me my center of pressure. It's a position, okay? I don't know why my font has gotten so bad recently, but Okay, so first of all, there's something you could see about, there's some constraints on the center of pressure. Since it's a weighted combination of all my forces, if I do have some number of feet on the ground, then I immediately understand that that center of pressure, that weighted combination of those ground reaction forces, will always be in the convex hull of the forces that I can apply on the ground. Right? So it's always going to be inside what they call the support polygon. Right? And then the magical thing about this particular point, this particular constraint, is that there's a constraint here on the center of pressure, but if the center of pressure tells me what's happening at my center of mass. Okay, this is the magical constraint. Do you have a question? Convex hull just means if I have a bunch of points here, or if I have a bunch of polygons, it's easier, yeah? Then the convex hull is going to be the polygon that surrounds it. Yeah? So the set, the two red objects do not form a convex set, but the blue object is a convex set. All right, so here's the big one. It turns out if you interrogate these equations and you think about what happens with the center of pressure, then you get this magic equation out, which is that mz double dot plus mg, that's stuck in there, times okay. The way that comes out, the way you derive that, is by understanding that there's a point on the ground where you can describe all these forces, okay, as a vector and a moment. And the point where that moment is zero, this is a zero moment point. So this is really the zero of a cross product. This is because the COP okay, and the derivation is actually simple, but for some reason, nobody understands it the first time they see it. It seems like, I mean, maybe there's someone out there that understood it, but I can't say unequivocally, but there's a lot of surprising amount of confusion about a relatively simple concept. So I decided, even though it's not hard, I decided I would not say it right here. I would put it in the notes, of course, for you. But let's just think about the implications of having this equation, and you can trust me on the derivation for now. Okay, it's in the notes if you want to see it. It's just a simple cross product argument, but somehow everybody gets confused about it, so I'll skip it. Yeah.
Can the center of pressure be above the ground? Like why there is a z component?
Good. So in the picture I've had so far, this is going to be the height of the ground. But it's important to sort of know the distance between this and this, right? So that's a constant in this picture. There's nothing you can do. It's just the height of the ground. So I wrote it as ZCOP, but the point is I need to know the height, the distance between that and the ground. Yeah. Okay, so this is a magical equation. It says that there's no moment. My forces can be summarized by a vector that has no moment around this point. Okay, but the implications are what I want you to understand. Is that somehow the dynamics of my center of mass, okay, and my inertia are inextricably linked with my location of my center of pressure, right? If I know my center of pressure, that implies something about my center of mass acceleration. If I know my center of mass acceleration, that implies something about my center of pressure acceleration. Okay, that's sort of maybe not surprising, but but for me it's surprising that a single quantity on the ground can tell me about the dynamics of my center of pressure, or my center of mass, okay? All right, so now let's start using this to our advantage, okay? So one of the things we said that is a common assumption is that let's make z double dot equal to 0. Okay, now remember there's a couple reasons to do that. One is that it simplifies the ground contact. It basically means you're not losing any energy into the ground. If my center of mass is actually never changing height, then I'm not gaining or restoring any vertical energy. So it simplifies contact, or justifies ignoring contact. Right? It also implies that this thing here is going to be, this thing here goes to some constant height. Right? That whole term is just a scalar constant height. Let's also assume for a minute that we can regulate our pitch, and we're going to set this thing equal to 0, too. Okay. Then now we're going to get something really nice and simple. Okay. What is it going to look like? It's going to look like the center of pressure relative to my center of mass is what matters. I get an mg center of pressure minus center of mass here. H mx double dot. Right. So I can cancel out my m's on both sides. And what am I left with? I'm left with, well, I could do it. It's x double dot is negative g over h, or x COP minus x. So this is still not a simple model. This is the true dynamics of the robot. If I have my center of mass up here, x, and z, or now it's at a constant height h, right? And I have a center of pressure down here. I guess center of pressure was red on the last time. Okay. This is my XCOP minus x right here. All right, so what does that tell me? So if my center of pressure is there, which direction is my, yeah, right? So if my center of pressure is out in front of me, then I've got a force pushing me backwards, right? And if I can do that in a way that my center of mass stays constant, then this is exact, right? So it means that if my center of pressure is in front of me, I'm moving backwards. If I want to move forward, I'd better put my center of pressure behind me, and I can start moving forward. Yeah. This is a fundamental property of pushing on the ground, right? It's true for a compass gate. It's true for a rimless wheel. Those guys are going to have trouble keeping their center of mass at a constant height. But the dynamics on the, before I made the simplification of z double dot equals 0, those are exactly true of any walking robot, or any robot pushing on the world, or whatever. As long as we're talking about contacts all in a plane, these are exactly the right equations. Okay, so why does this matter? Why does this help? Well, first of all, if I know, I was able to write, I wrote a lot of sort of complicated constraints on forces, right? If I have friction on each potential force and they're in different locations, I've got R cross F everywhere, right? I can sort of simplify this whole thing. I simplified the constraint on the center of pressure to be inside the support polygon. That now implies a very simple constraint on my acceleration. Okay? And because it's a linear relationship, that's an easy mapping. Okay. What's more, it turns out this gives me an extremely simple way to generate feasible contact sequences and feasible plans for my center of mass relative to my center of pressure. Okay? Right? Because that relationship is just some linear second order differential equation. Okay? So the problem of the satellite, we have to decide when to move things around, is scary and hard and has this discrete component, it has all these other components. But somehow, if things are all in the plane, that's the only simplification we sort of made so far, that where center of mass stays constant, our contact points are all in the plane, then I'm going to have a very simple algorithm for that to pop out. Okay? All right, so here's the most common way to do it. There's lots of ways you could potentially constrain one or the other, but here's a very standard way to do it. So a lot of times, if you're a walking robot, you'll look down at the ground and you'll come up with some, you'll have constraints on where you can put your feet. Maybe there's stairs, maybe there's something else, okay? So the most common approach is sort of step one, choose some foot placements. Okay, so maybe if I have square or rectangular feet, I'll go ahead and make a plan that puts my feet down. Okay. This is now looking down from above at my foot. Yeah. And then, given a set of feet, I know instantaneously what my constraints are on my center of pressure. Right? I could just say that if this foot is the only foot on the ground, my center of pressure has to be inside here. Okay. If this foot's on the ground, it has to be inside here. If both feet are on the ground, I can put it anywhere in the convex hull. Right? And what's more, there's this notion of if your center of pressure is more inside your foot, then you're going to be a little bit more robust because someone could come up and push me, give me move my center of pressure by accelerating my center of mass, and I'm not on the verge of instability. Okay? So a very common recipe here is to take your initial footsteps and now step two, choose, hard code, a trajectory of my center of pressure. Because I have good heuristics for doing that, right? So when I'm standing on one foot, I want it to be roughly in the middle of that foot, okay? When I know when I'm standing on this foot, I want it to be roughly in the middle of that foot, and I'll just keep it right safely in the middle of that support polygon. I'll draw a straight line. During double support, I'll move it from one point to the other point, and then as I put my other foot down, I'll start moving it here, and then I'll lift this foot up, and I'll have it here for a little bit, and then I'll move it here. Right? I can come up with a trajectory, hard code a trajectory for my center pressure, and the picture doesn't show it, but the timing matters a lot. But simple heuristics sort of, keep it in the foot completely while you're on single support, put my other foot down, we'll sort of speed it up, slow it down over to here, pick it up, put it down, speed it up, slow it down over here. I can hand code a trajectory of the center of pressure that's going to work really well for my robot. Okay? This is a very different view of planning than anything we've talked about so far, right? So this is, we're talking so far, let's formulate an optimization, search over joint trajectories for my acrobat. get it up to the top. I'm going to hand code the contact forces that are going to control this thing. I'm just going to hand design it, and I'm going to read back what that implies as a constraint for the rest of my system. Okay? It's a very different view of the world. It's a very powerful one. Okay? And then what I can do after that, once I have a center of pressure trajectory, I can integrate these dynamics forward to come up with my center of mass trajectory. Right? I guess I get a new color. Right? Now, if I know the center of mass at time 0, it's literally I can just differentiate the second order equation and solve for my center of mass dynamics. But we know some control, so we can do better. Okay? This is a linear equation, a linear second order differential equation. I can not only solve this, but I can solve it. Even if you give me an unsatisfiable center of pressure, I can even design a feedback controller for it. Okay, so let's just see how that plays out. Right, so let's think about my mapping from CO pressure, center pressure trajectory to center of mass trajectory. Okay, so I'm coming in with a desired center of pressure over time. Let's make a planning problem where I have Q is I'll do it in 3D here, even though I've drawn everything in the plane so far because it's easy to do in 3D. Let's say I've got my X center of mass and my Y center of mass. Okay, the dynamics of this thing are something that I can write down. Okay, this is the first time I'm going to make an assumption, make a simple model. Okay. Let's assume that I have the ability to move my center of mass around. Okay? So this is now a simple model. Which makes sense if I have a big complicated robot like Atlas or Asimo or Hubo or HRP2 or whatever, but it doesn't make as much sense for a compass gate. Okay, and I can put down extra constraints. I can list all my constraints on Q double dot if I like. But it turns out if we've designed our center of pressure trajectory, we can often get away by ignoring these constraints. Okay, and then my true, given my acceleration Q double dot, I can always extract my true center of pressure, which is going to be my H over G Q minus U. Right, I can always back out. I just inverted the equation from before. Right, I just moved X double dot over to here and X center of pressure over there. So I can always back out what my center of pressure is. And importantly, this is a linear function of my current configuration Q and my current input U. Okay? So what do I have now? You should be thinking, I have a dynamical system, which is a linear system. and I have sort of an output, which is a linear function of my state and my control. Yeah?
Sorry, can you just show us how you got to that XCOP expression? And then also, you switched from Z to Y, I think. Just to clarify.
I did switch from Z to Y. No, I didn't. That's correct. Right. So no, it's the same. It's the same thing. But Z is up, and I said that I can go ahead and think about my center of pressure in both the X direction and the Y direction. Yeah. With no extra. I could have just left it as XCOM and we'd be fine. But just knowing that it generalizes trivially to the solving both of them at the same time is nice. Okay. And how did I get this equation? So
You're plugging in QW dot equals U.
I have the relationship between, so I'm really just moving X double dot over here, and then nope, and then moving X center pressure over here, and then I plugged in U for this. Yes, good. Okay, so I got myself a linear dynamical system that describes the evolution of my center of mass, and an output equation, which is a linear function of my state and my input. Okay. So now if I want to solve, for instance, if I want to minimize over U of t, for instance, a quadratic cost, the difference between my center of pressure and my actual center of pressure over some trajectory. It's just an LQR problem. Okay. I can write this down as this cost function. I can write down as just a full quadratic form. It's just a quadratic because I've got a linear function here. The squared term gives me a quadratic function. It's quadratic in X and U. The only thing that's different than what we talked about before was that because I have some of these affine terms in here too. It's a full quadratic form. Yeah.
Sorry, sir. Unless we're missing something when we solve the XCOP, we just do that Gaussian transformation. The H over G only applies.
Yeah, I thought I sort of caught that too. So good. So it should be. Is it missing a minus sign too? Okay, so H over G equals center of pressure and then plus U. But I think it should be plus U. Yes, good. So it's this, yes?
Well, I get a minus.
So the minus is that of H over G.
Good. It's hard on 2 slides. Good, thank you. All that matters is that it's linear.
Yeah.
No, I'm glad you're catching it. Yeah. Tell me what it is.
So I get XCOP equals X minus H over G.
X minus H over G U.
Yeah. So and then X would be Q minus H over G.
Yeah.
Q minus H over G U. Thank you. Good. Still linear. Okay? My apologies. All right, so this is a big deal. This tells me that if I have a center mass, okay, and some trajectory, I didn't actually derive it, but it's in the notes, but it turns out you can solve LQR even if you have these other terms sticking around in there too, okay? This thing is often called the linear quadratic tracking problem. So linear quadratic tracking. But it's right in the LQR notes chapter, and it's just a minor extension where you have these extra terms to cancel, but the Riccati equation idea still works, okay? So what does this give me out? This tells me, remember, my control input is the acceleration of my center of mass. This says if I have some desired center of pressure trajectory, then I can define the dynamics of my center of mass by solving an LQR problem. The solution takes the form, right? The solution of this equation is going to look like an LQR thing, right? So it's going to be an U0 minus K x minus x nominal. Okay, it's going to have a term. It's got an extra term kicking around, plus possibly K1. Okay, but it's just a linear function, but it's a feedback controller, right? So if I have there's a couple things that come out. First of all, I have a center of mass trajectory that comes out, which I could get just by integrating this forward. It tells me what I should do from a particular initial condition, what I should do to try to regulate the center of mass. But even more so, if I get knocked around and I'm still trying to keep my center of pressure trajectory regulated, then this is a feedback controller that will tell me how to regulate that center of pressure trajectory. And I threw away the constraints to make it an LQR problem. But if I stay sort of safely inside if I choose my plan like I did on the last step, right, then that's why this margin matters, is I can stay away from my constraints. And what I'm going to get out is a nice center of mass trajectory that will match as close as possible the desired ZMP trajectory, center of pressure trajectory, okay? And it's going to look, if I start with my center of mass right over here, if I'm moving slowly, it actually follows, you can imagine if I move arbitrarily slowly, then it's going to have to just be right on top of my center of pressure, right? And as I start moving faster and faster, it's going to come up with this nice sort of exactly the right thing. It's going to give me a center of mass trajectory that doesn't have to go all the way to my foot. I'm going to accelerate, lean into this, come back, lean into this. And ironically, walking faster can be easier than walking slowly because you have to move your center of mass a lot less, right? We actually saw that in the DARPA competition. We had our controller was kind of struggling to walk slowly, and then we just ratcheted up the speed, and everything got a lot better. Yeah. And then at some point, the simulator stopped working. The simulator we were given, and the robot's legs started deflecting into themselves, and we had to stop. But it was kind of fun to see how fast you could make it walk. All right, so the point is that if I'm willing to now use a simple model, the only simple model, the dynamics of the center of mass and center of pressure are real. They're general for an arbitrary robot. The simple model assumption I've done here is that I can produce arbitrary acceleration of my center of mass, right? So if I have a robot that can sort of produce an arbitrary acceleration of its center of mass, and I can put some constraints on if I like, but the problem gets a little bit harder, okay? Then planning a dynamically feasible motion for a walking robot is basically as simple as solving an LQR problem. That's amazing, okay? It's actually even a really simple LQR problem. It turns out that since A is trivial, it's just a simple second order system, we don't even have to integrate the Riccati equation numerically. We can solve it in closed form, okay? That's one of the things that we did to make our planner really fast for the DARPA challenge. Okay, this is an idea that's been around for a while. Honda, when they debuted their humanoid robots in the late 90s, 97 was the first time I saw it, were presumably doing something like this. The people that made it clearer, at least in my mind, were doing so in 2001 was when their papers started coming out, but this is in 2003 is a paper that really does a very nice job of it. Lots of people have written similar things. this is the one that actually uses LQR initially first. And they show their humanoid robot with constrained footsteps, which is a big deal. Right? They write down the equations of motion. And they have a desired ZMP, which you should think of as center of pressure. ZMP are the same in these cases. And the center of mass trajectory that comes out. Okay? And they can do it for complicated turning, you name it, right? So if I have stairs, I can come up with, now the center of, this, remember we said a constant center of mass height was the simplest thing. It turns out if z double dot is constant, that's what really matters. So I can also solve these questions easily if I have a sloped center of mass. Yeah.
So do they know the model of the terrain?
Say it again.
Do they model it?
Yep. This is the terrain is known. You choose your footstep ahead. Hard problem. We haven't told you a solution for that yet. But if I put some down, then I can, and I just hand prescribe the center of pressure trajectory, then I could solve the center of mass trajectory and solve it very fast.
So the constraint there is you always have to keep your center of mass within your support polygon of your current.
And a heuristic is keep it in the middle of your support polygon, because that somehow will give me a little bit of room to wiggle room if someone pushes me, or if I have a model that's wrong. If I center, if I
So are you really planning on
sorry,
Not center.
so they're related, obviously. So this, you want to keep your center of pressure in the middle, and then that implies that your center of mass stays near the middle. Yeah. Okay. I should say center of pressure.
So you're really planning on the center of pressure trajectory, and then that using the equation tells you where your center of mass has to be going.
Yes.
But you want the solution that have the property that the center of mass stays within your support polygon.
Yep. Yep.
But you just do that.
Sorry. Your center of mass does not have to stay. That's why you're pointing it out.
Center of pressure.
Yes, but it's actually, it is very important to point out that the center of mass does not have to stay inside the support polygon. That is a very key point. In fact, I should have emphasized that. So the initial robots that came out had a constraint that their center of mass was always over the support polygon, and they were horrible. I mean, they sort of, it means moving like this, right? Kind of, painful to watch. It's called static walking. This is not a static gate. Your center of mass can move outside your support polygon, but your center of pressure does not. Right. So here's the output, and I'll tell you about some of the other pieces in the middle too. But the output is that we have basically an instantaneous planner that will plan a whole body trajectory for our humanoid robot. Okay, so there's a couple extra pieces about how do you go from center of mass to a full kinematic model, to all your joint angles. I can tell you about that. It's another optimization. You won't be surprised. Okay, and there's a couple extra pieces, but all of them are super lightning fast, right? So this is actually running more machinery than I need to. It's running it in MATLAB. It comes up with this plan basically instantaneously, and then oh, damn it. I reset my network. Always. LCM. Okay, here's Atlas. Let me steer back around here. It's got some nominal walking parameters here. I'm not used to using the mouse anymore, but okay. Here's my footsteps. This is the blue is my ZMP trajectory. The green is my center of pressure trajectory. And this thing, in all that time, not only computed the center of mass, but it also computed the whole kinematics of the robot, an entire plan. This is a nominal footstep plan. Just move your foot up in the Z direction. Can you see that? That's my footstep plan. And I can play it out. Off we go, walking. Full body motion plan, on demand, hitting footholds as necessary, real-time planning.
Is this part of the matrix?
Yeah, it's in there. Yeah. Okay. So yeah, but you have that example. It's just in examples atlas. Yeah.
So if your center of mass is outside of your center of pressure, like in the head, so you're falling forwards, how do you prevent yourself from your center of mass having like this acceleration?
You put another foot down in front of you, basically. Basically, you're allowed to leave, but you better have a plan going forward that's going to catch you, right?
Without ever moving your center of mass up and down, which was your assumption, this work.
Yes.
So like if I'm taking a step and falling forward, so I have to be like raising the barbell at the same time to like keep my center of mass constant height.
Yes. Right. So hopefully not a barbell, but we definitely had some initial when we first started playing with this, and you just before you understand the parameters of your robot, we asked for the center of mass to sort of be kind of high, and we had walking that went like. Right? We called it happy walking, but the arms always went up in order to keep it sort of center of mass. They're heavy arms, so you can get a lot out of that, But yeah, but then you find the nice sweet spot, and those go away, right? Okay, so the cool thing is, this is all parameterized. I want you to understand it's parameterized. Well, here's Robin's footstep parameters. There's, you can say step width, all these different things, right? So let's crank up the speed a little bit, huh? I won't do that to you, but let's make it quite a bit faster. Okay, so what you should see here is that now the ZMP is the same trajectory, only the timing is different, and the center of mass has to move much less to get that, right? See that? And off we go walking full body, on the fly planning in MATLAB, with some mechs underneath. But all right, let's see what we can do here. I already changed the other parameters, Robin, if you're worried about it. The minimum step times and stuff. Robin can make that look a lot better than me, but in fact, we got it up to 5 meters per second in the virtual challenge. Okay, but the amazing thing is that this would work even if the footsteps were constrained, right? If I was walking on stairs, if I was walking on those other footholds, it works. It's fast. Now you could ask, am I happy with that, right? So am I happy with keeping my center of mass at a constant height? Well, so if I need to move on demand and don't want to wait for it, then I'm going to be happy with it right now. But really, to do more dynamic, more interesting motions, to be more efficient, whatever, if I'd like to have a better or more aesthetic plan, whatever, then still there's a huge role for this to play because this gives me an initial dynamically feasible plan for a humanoid robot just like that, right? And if I take that as an initial guess and hand it to a trajectory optimization that's thinking about the more complicated dynamics, removes all the assumptions, then I've already given it an initial feasible seed. It doesn't have to start from scratch. Okay. All right. So let me tell you a few of the other details that make this work, and we're almost out of time, so I'll do them. But I do want to sort of give you a sense of just what the other pieces of the puzzle are there. Did anybody have any questions about that? Oh yeah.
So the sleep model and this is complementary, or how does that?
So there are people, for instance, that instead of this idea that I can just accelerate my center of mass arbitrarily, that's often called the linear inverted pendulum model. Okay, so you think of it as a card on a table. There's a couple different names for it. Okay, that is one choice. Is that let's keep the center of mass constant and assume I can accelerate the center of mass. Slip is somehow a different model. There's a paper that there's people that for instance will try to make the center of mass look like a slip trajectory, and then use some of the dynamics we have for slip to try to solve for the long-term dynamics. If you wanted to make your robot run, that might be an idea. It's not my favorite idea, but because I don't think that the humanoid should necessarily look like slip, where I feel like this is really the dynamics of the humanoid. And then my only assumption is that I can accelerate this directly. my objective might be wrong, but the dynamics are sort of real. At the slip, I worry that you're sort of imposing pogo stick dynamics when the robot might not be very good at that. But you could take that and impose that instead. Right? So that's the way to relate those ideas. Yeah.
So we don't have any guarantees yet that the trajectory for the center of mass is feasible.
So only by being conservative about our choice of the ZNP. If you want to solve a slightly harder problem, then you can add these constraints in and then solve a convex optimization to solve this problem. Right? You can do linear model predictive control. You could solve a big quadratic program to come up with the trajectory, and maybe you have to do it at every time step to get a feedback controller out.
You cannot be accurate with that, right?
So okay, there's a question about the how can I write down my constraints on the acceleration of u given the constraints on the whole body? That's a harder problem. But even at this level, there's some constraints that could be that we've ignored, and we could put those in. There's one level of complexity up, which putting in the acceleration constraints that we talked about already. You know, can't go outside my 4 polygon or the like. That you can solve easily with linear MPC. If you want to start putting torque limits mapping to acceleration limits on my center of mass, then you get the nonlinear dynamics of the robot involved, and you tend to end up with a nonlinear optimization problem. So one of the things we've been working on in the group to make those monkey bar videos and jumping down from boxes and the like is we use both the sort of center of mass dynamics and the full kinematics of the robot. And we don't assume this, but we compute u, okay? And that allows us to sort of handle the kinematic constraints. So for instance, Robin always wanted to walk sideways through the doorway to be able to come out. And you know, we're finding ways to put in pieces of the whole body problem without taking the entire complexity of it. And that's, I think, an active area of research. Okay, so how do I map this down to my full body coordinates? Well, the basic idea is that if I know where my center of mass is at any given time, and I know where my feet are, then I have a kinematics problem to solve. This is the inverse kinematics problem. Find a solution of joint angles where my center of mass is where I said it's going to be, and my feet are where they're going to say they're going to be, and maybe that's not enough to constrain it. You don't know what your arms are going to do, for instance. So the way we formulate it as another optimization problem, which we solve for every time step, which says there's some comfortable position for the robot. Okay, this is my nominal position for the robot. Be as close to possible to nominal, subject to the constraints that my center of mass is where I said it's going to be, and my feet are where it said it's going to be. And that gives me a nonlinear optimization, but one that I can solve quickly with SNOPT. So we literally called SNOPT a lot of times to make that trajectory come out, and still in the blink of an eye. The trajectory optimization we did before had dependence over time, right? It had to solve a long-term optimization problem. This instead has lots of instantaneous optimization problems. They're relatively very simple optimizations. And then to actually execute it on the robot, we would do more. We would take, and maybe I can write this down a little bit carefully. This is what Scott started to tell you about before we had all the machinery to tell the story. But just to control the robot, right? We can form another optimization problem, which I want you to think about it as doing what you did for problem 4 on the midterm, right? Which is I've got some Lyapunov candidate. The Lyapunov candidate we have here is a LQR cost to go function on my center of mass. But I've got a whole robot, so the constraints on U are tough, right? So what I'd like to do is I'd like to go downhill on my cost to go for my LQR controller as fast as possible, subject to the constraints that there's friction cone constraints, that my U constraints are hard. And that's something we do solve at real time on the robot. And it looks like this. At every time step, we minimize with decision variables, Q double dot, tau. This is now actually for the whole robot. and contact forces even. The difference between my desired center of mass, I'll call it P, just so I want to keep it distinct from that. Torques. Okay. Plus some term that says my foot's going to move in a certain way. Let's say, for instance, my double dot of my foot. Again, this is a function of my whole joint angles. I have some desired trajectory of my foot. This desired trajectory of the center of mass comes from the LQR controller. There's lots of tweaks on this. I'm just trying to write the simplest one to understand. Okay. And I have additional constraints that my foot moves in some particular way. And then I'm going to subject that to all the constraints of my robot, right? So for instance, the most important one my manipulator equations. Okay, I've got contact force constraints. This is the answer to your question, is how do I take in all those different constraints into account? I don't at the planning phase, but at the execution phase, I try to execute my feedback plan as well as possible, given all the instantaneous constraints on the robot. Okay? And the magic here is that if I know Q and Q dot, because I'm in that state right now, then the rest of the dynamics, this is all linear in the decision variables. And I can actually solve this big scary thing to try to find an instantaneously good control input, U, as a quadratic program. I know I'm going fast. This is just to give you a sense for how these things snap together, but the center mass planning story was the story I really want you to get out of the lecture. Okay. So again, we're still thinking about this as LQR planning for the center of mass, and then another optimization that makes it feasible and executes it on the real robot. Okay? And there's even yet the other optimization, which is that inverse kinematics optimization.
LQR part, you're assuming, that's assuming you just command acceleration from the center of mass, and then you figure out how to do that with a static optimization.
Yes. That's the current recipe.
And this is, so the LQR control, you can't duplicate that. You have to know where your current state is, so you have to solve. This is fast enough to be solved.
I can solve the LQR arbitrarily fast. That's
This step.
and this step.
Once I get an LQR control input that I want to do, I have to actually do that. You can't pre-compute that.
It would be slow to include all these dynamic constraints in my. It would not. It would no longer be LQR.
Yeah, no.
Yeah,
But I'm saying, is this second step fast enough that
This step I can run for one state of the robot online at 500 hertz or 1,000 hertz or something. We had to work hard to make that true. It involved late nights, moments before the competition, but writing new solvers and the like. But yes, we can solve it fast. Okay, so stepping back. So this in this special case of walking on flat terrain, my satellite with moving thrusters picture, all those thrusters can be summarized with the single point, which is my center of pressure. That's surprising, and it turns out to be surprisingly useful because of the connection between the center of pressure dynamics and my center of mass dynamics. I can prescribe the forces that I'm executing, that I want to execute, and read out the position that my robot has to go through to do that. That's the big idea, right? Is that it turned out to be easier to plan my contact forces first and then reason about what my robot had to do to make that contact work. So if I'm thinking about a parkour robot that's about to just jump around this room or whatever, the strategy, the extrapolation of this would be, don't think yet. The first thing you should think about is not how's my leg going to clear that, right? The first thing is, if I'm going to get over there, I'm going to need to put some force on right around where you guys are sitting. Sorry about that, right? And then I'm going to put a little bit of force over there, and then a little bit of force over there, okay? And then I'm going to, in a second pass, I'll clean up and figure out what my robot had to do to make those forces happen. And that turns out to be a different view of planning than what we're used to, but the surprisingly effective view of planning for constrained footstep planning and whole body motion planning on robots. And there's a big question then of, the foot planning problem is super tough. Robin's making an incredible dent at it. The problem of push recovery. I'd like to have a robot that if I push it a little bit, it goes like this. If I push it more, it takes a step, right? I'd like all that to kind of fall out of these high-level planners. I'd say that's still hard. Although Tuan, who's up there, has a really nice paper on capture point that I'll cite in the notes that has really nice mechanical insights about that and get your head around that picture. Okay, and I think the types of, you could imagine running Robin's footstep planner fast enough that it runs online and get sort of something like that out. Okay, there's really hard. I still think the satellite problem with moving thrusters is not solved to my satisfaction. But if you're willing to prescribe the trajectory of the thrusters with a heuristic like this, then reading out the motion of the satellite works. Good. It turns out that story is going to generalize very nicely into manipulation. Thinking about contact forces first, and we'll talk about that on Thursday.